Classical mechanics problem, example problem of Newton's second laws in other coordinate systems. Let's do it. So let me explain the problem and then I'll tell you, I'm going to give you a map out of what we're actually going to do. So the problem has a mass stuck on the surface of a cylinder. There's no friction, a vertical cylinder, and the mass has to be on the wall of there. So it can move around and it can move up and down. And we want to get an equation of motion. We want to model the motion of this. In this particular problem, the cylinder has a radius r, it starts at height h above the ground, and it has an initial angular velocity of omega 0. Now, we're going to use cylindrical coordinates here. So we'll call this the z direction, and then we'll use in the vertical, looking at it from the top, here's x, y, we'll use r and theta to find the location of that. So r, theta, and z were our coordinates. Why couldn't we use Cartesian coordinates? Well, imagine that this thing's moving around in the x, y, z directions. Well, I don't know the magnitude or direction of that normal force that constrains the mass on the surface of the cylinder. And I can't really, it's really difficult to incorporate that into a solution. It's not impossible, just difficult. So here's what I'm going to do. I'm going to set this up in cylindrical coordinates. I'm going to skip over the derivation of acceleration in polar coordinates. I have a video about that linked down below. And then I'm going to build a 3D model of this cylinder with the mass moving on it so we can see what its trajectory looks like. And then I'm going to show you a second way of modeling that motion. And then we will use Cartesian coordinates in that case, and it's going to be fun. Okay, let's get to it. So the number one thing, I want to write out the acceleration in cylindrical coordinates. Okay, and remember, the problem is that we have these time derivatives of the unit vectors in the r hat direction and theta hat direction that make it very difficult, but not impossible. So the acceleration in cylindrical coordinates is going to be equal to r double dot minus r theta dot squared r hat plus, I forgot it already, 2 theta dot r dot plus r theta double dot theta hat plus z double dot z hat. And just a reminder, r double dot is the second derivative of r with respect to time. So the dot notation is a way to represent derivatives with respect to time. I mean, we're going to use that a bit, and if this is your first video, I apologize for jumping right into that, but it is important. Okay. So if I have the acceleration in these coordinate systems, I can write Newton's second law for the r hat direction, theta hat direction, z hat direction. Let's do that. So in the r hat direction, I have F net in the r direction. What forces are going to be acting on this mass? Well, I have this normal force that way, and I have gravity acting down. So it would just be this normal force in. And I don't even know the direction. It could be positive or negative. I don't even know. And that's going to be equal to r double dot minus r theta dot squared. However, I do know something very, very useful here. And that is that r, the r value, is equal to r, the radius of the cylinder. Okay, so if I take the derivative r dot, I get 0. If I take the derivative of that, r double dot 0. So this is just going to be equal to n is equal to negative r theta dot squared. Okay, now let's look at the theta hat direction. F net in the theta direction is going to be, again, r dot is 0. So it's going to be 0 plus r theta double dot. And what forces are in the theta hat direction pushing it around the cylinder? There are none. So this is equal to 0. And here I have theta double dot. I can divide both sides by r. I get theta double dot is equal to 0. We're going to solve that equation, but let's first look at the z direction. F net in the z direction is going to be negative mg. It's the gravitational force, and that's equal to mz double dot. Again, the mass cancels. That's nice. And I have z double dot's negative g. But let's solve this equation right here, because that's the solvable differential equation. If I integrate both sides of that equation, I get theta dot equals a constant, C1, I'll call it that. Because if I integrate this, I get theta. Remember, the fundamental rule of calculus says that an antiderivative and integral is an antiderivative. So if I integrate that, I move up, but then I have an integration constant. Let's find that constant. So theta dot at time t equals 0, time t equals 0 is the initial angular velocity, omega 0. So I know that. Now let's find theta as a function of time by integrating again with respect to time. So theta as a function of time is going to be equal to omega 0 t plus another constant, C2. Let's put in theta 0 as omega naught times 0 plus theta naught. So now I have theta as a function of t is omega naught t plus theta 0. So I have my theta equation of motion. That's pretty nice. Let's do the same thing for z. So I'm going to integrate, if I integrate z double dot as negative g, I get z dot as a function of time is negative gt plus a constant. I'm just counting up my constants like that. If I put in my initial z velocity for c, if I put in t as 0, that gives me my initial t is 0, that term goes away, so that would have to be my initial velocity. So this is going to be equal to z dot as a function of t, negative gt plus vz, 0. That's my initial z velocity. Now I can integrate that again, and I'm going to put it over here because I'm running out of room, and I get z as a function of t is negative 1/2 g t squared plus v0 z t plus another constant, C4. And if I put in t equals 0, then C4 would have to be equal to the initial height, which we're calling h. So now I have an equation of motion in the z direction. I have equation of motion in the theta hat direction. And then the r direction doesn't change, it's constant. So I can model the motion of that. That's the end of that problem, right? I solved it fairly easily with these two equations. Now for the fun part. Let's model this numerically. So to do that, I am going to need some values. I have g, the value of the gravitational field. I'm going to need the radius of the cylinder. Let's say it's 0.1 meters. Let's say h is 0.1 meters. And let's say omega 0 is, let's just put it at 1 radian per second. I don't know. We'll change that. But I need those values so I can do this. Because over here, and theta 0 is 0. So theta 0 is 0, omega 0 is 1, v0 is 0. Okay, let's go ahead and do that and make a 3D animation. It's going to be super awesome. You're going to love it. I think you're going to love it. I'm going to like it, and that's really what matters. Switching over to WebVPython as usual, completely blank slate here. Let's make this a little bit bigger. Let's enter our constants. G equals 9.8. So I'm using the constant g, right? I'm not using the vector g. R equals 0.1, h equals 0.1, and then what did I say? Omega 0 is equal to 1, and then vz 0 is equal to 0. T equals 0, dt equals 0.01. Okay, so now what I want to do is make a cylinder. So let's just make the cylinder. I'm going to call it thing. Thing equals a cylinder. The position is going to be equal to vector 0, 0, 0. The radius is going to be 0.1. The axis. So a cylinder works by a couple of important parameters. Position is the location of the center of the cylinder at one point. Axis is a vector from that point to the other end. Okay. And then the radius is the radius. So in this case, what I want to do, I'm going to put it in the y direction. So my gravity is going to be in the y direction, even though I did it. Well, I didn't say it wasn't. I guess I kind of did. I said z. because Z is in and out of the board. I want the cylinder to be up and down like that. So my axis is going to be equal to, I didn't say how tall I want the cylinder. Let's put it at 2 times h. So it's vector 0. No, I want it in the y, in the y direction. 0, 2 times h, 0. And then finally, I'm going to put one thing, opacity equals 0.5. So it's kind of see-through. Let's just see if this runs, because you should always run things before you get too far in case something bad happens like that. Oh, there it is. There's my see-through cylinder. Okay, now I need my mass. Let's call it a ball. It's a sphere. Its position is going to be equal to vector. Now I know theta. Let's put theta 0 up here. Theta equals 0. I'm going to enter this in terms of theta, which is kind of weird, but I'm going to do that. So this is going to be equal to r times cosine theta. The y direction is going to be h, which I switched, remember, and the z direction, oh, that's capital R. R sine theta. That's the position. Now the size of that, how big should we make that? Let's see, radius equals, let's say R over 20, color equals color dot yellow, and then make trail equals true. We obviously want to leave a trail. And there it is right there. Okay, I drew it the other side, it doesn't really matter. Okay, I might go a little bit bigger. Let's see, radius divided by 12. Let's see. Oh, not 212, 12. Okay, that looks good. Okay, so now we're ready to animate that. If I calculate the vertical position and the theta value, then I can do that. I can plot out wherever it is. So let's make a loop while t less than 1, rate 100. So rate 100 says don't do more than 100 calculations per second. So the first thing I want to do is to calculate the value of theta. So if you look over here, I have theta as a function of t. If I know t, I know theta. So let's just calculate that. Theta equals, I'm going to put this as theta 0 because I used it in my equation up there. It's going to be equal to omega 0 times t plus theta 0. That's just my equation motion right there. You can't see it because I'm pointing to it, but it is. And then my y value, which is not my z, but it looks like my y. So let's say y equals h plus vz0, which I called it z, I don't know why t, minus 0.5 times g times t squared. So there's my position there. Let's put the ball at that location. So ball.pos equals vector r times cosine theta, y, r times sine theta. This is just for animations. Now I'm going to update time, t equals t plus dt, and let's run this sucker and see if it works. It might not, you never know. Why is it so slow? What did I do wrong? That's weird. Maybe why? Oh, I updated t. Let's just print t. Ball y h t. Something weird's happening. It's printing that. What if I don't do this? Because it made my cylinder go away. I think where's my cylinder? Let's see. Okay, we're troubleshooting here. This is a good thing. Helps us learn how to troubleshoot. I'm going to comment out that whole section and see if it's something that tells me where I messed up, right? So I'm going to run this because it was working. Okay, that's working. But where's my ball? My ball's gone. Ball.pos. I had it working. R. Why didn't that print? Let's see if I just comment out that. Where's my ball? Okay. Let's just put another ball. Ball equals sphere. Position equals vector R 0. Radius equals R over 12. Color equals colored dot yellow. And you may be oh, this is so annoying, but I think troubleshooting is an important part of learning how to do all this stuff. So there's my ball. Okay, so that worked. So why is this not working? That ball is not working. Sphere position is vector R times cosine theta HR times sine theta. Radius R over 12. Color equals color dot yellow. Make trail equals true. Okay, let's just start deleting stuff. Okay, now let's see if that makes it. I don't want two balls though. It's gone. Why is my position equals vector R? Oh, I got rid of theta. That's why. Okay. Theta equals 0. Okay, got it. So that's what happened. I changed theta to theta 0, and now I can put this stuff back in here. Color equals color dot yellow. Make trail equals true. And now I can comment the stuff, uncomment the stuff. I don't need to print T. Okay, now let's run it. That's a fine little diversion there, wasn't it? Okay, so it just drops straight down. Let's run it for a shorter amount of time. Let's just run it for 0.1 seconds. Okay, so it does seem like it's working. It's not, my angular velocity is not high enough. Let's increase that to 3 and then run this for 0.2 seconds because, yes, it drops pretty fast. Okay, it's working, right? Look at that, it's working. Let's increase my omega 0 to 6 and see what happens. And you can see it is indeed staying on the cylinder. Now let's just do something fun. I want to give it an initial velocity in the y direction of, let's say, 0.5 and run it. Okay, so that's pretty good. It's stuck on the cylinder. I'm pretty happy. I want to go a little bit faster. Let's say 10. And let's make this 0.8. There we go. Pretty cool. Okay, I can run that for a little bit longer, 0.3 seconds, but we did it. And it goes below the cylinder because it doesn't know any better. Okay, now what we're going to do is to make a second ball. And in the second ball, I'm going to model by having it connected to a spring in the XZ direction, right? And so I can calculate the force on it. I don't have to find the force of constraint. I can model the force of constraint as with the spring. So let's just do that. In this case, I'm going to have to make a second ball. It's going to have a mass. Let's say it has a mass of 0.1. I need a spring constant. I'm going to start off with 500. Let's just see if that works. So ball 2 is equal to a sphere. It's the same thing. So let's just copy this. I want it to be a different color though, of course. Ball 2 is sphere, position, same everything. Color is cyan. Now, I do need to give it an initial momentum because I'm going to change the momentum once I calculate the force. Ball 2 dot P is equal to M times vector. I want it to have the same initial condition. So its x velocity is going to be 0. Its y velocity is going to be vz0, right? It's the same. And its velocity, no, it's yeah, and it's moving in the z. Which one way was that moving? In the negative. z direction. So it's going to be negative r times omega 0. That's its initial velocity. I think that'll work. Okay, now down here, I want to calculate. I'm going to do this a little bit differently, right? I need to know how far it is from the origin in the xz plane. So let's make a variable called this rxz, and it's going to be equal to vector ball2.pos.x 0 ball2.pos.z. So it's the xz value. I can use that to calculate the force. F is going to be equal to, this is just the net force. It's going to be equal to negative k times r minus the mag of rxz. Is that right? So if it's greater than r, the force should be pulling back. Yeah, that's right. Okay. And then I need to multiply that by the norm rxz. So that makes it a vector again. Now I have the gravitational force plus m times vector 0g 0. So I didn't have g as a vector, so I had to add it in there. Now I can use that to update the momentum of my ball. Ball2.p equals ball2.p plus f times dt, and then update the position. Ball2.pos, ball2.pos plus ball2.p times dt divided by m. And that should move the ball, right? And then the other calculation is the same, and that should work. If this doesn't work, I'll be a little bit sad, but it'll just be another opportunity to troubleshoot. Okay, I exploded. I suspect I have my negative sign wrong here. I do that sometimes. Oh, this is negative g. There we go. Okay, so I had to go the wrong direction. So my initial velocity over here, when I made it, this should be positive. Pretty much the same. Not exactly the same because of my time step. So I could increase my, one of the things you'll notice is that if I look at this from the top, you may see that it's going in and out of the cylinder. My spring constant might not be high enough. So let's just change this to 1,000. Let's make the time step smaller. Let's make the rate faster. And then I think we'll get a better agreement. There we go. Identical. Pretty happy. Okay, that's it. That was fun. I don't know if you had fun, but I had fun. The end.